Hello, my name is Laura Cabrera and I am with Wizard Corp, and today we are going to be taking a look at artificial blood vessels. When looking at creating artificial blood vessels, one of the very important things that needs to be considered are the kinds of materials that the blood vessels are going to be constructed out of. The material used in a project like this, some of the criteria that they must meet is first and foremost to be biocompatible, because this material needs to be able to survive the varying blood pressures that are produced by a human body. The models constructed in this project were then ran through a simulation that was modeled after the human heart of an adult male. And the last criteria would be for the material to be cost efficient in order to be able to reach all kinds of population given their economic standpoint. For this project, materials that were selected included polyether ether ketone, or PEEK, which is a bioactive polymer. This polymer has a chemical structure that is able to withstand high temperatures and any kind of damage that might have been caused by chemicals or radiation. It also has a strength that is greater than most metals. The second material selected was polyethermide, or PEI, and polyethermide is another thermoplastic that allows for growth of the fibroblast cells and endothelial cells. Fibroblast cells play a critical role in wound healing, and they are able to synthesize extracellular matrix, which help close wounds. And the endothelial cells line the interior surface of a blood vessel and form an interface between the vessel itself and the circulating blood. The last material used in this project is polytetrafluoroethylene, or PTFE. PTFE is a polymer material that is able to provide resistance to any kind of chemical damage and also has a low coefficient of friction. It is also able to promote cell growth such as fibroblast and endothelial cells, just like PEI. With the material selected, the SolidWorks models were then able to be created. These models were created with the dimensions that were found for regular blood vessels found in the human body, which include an inner diameter of 6 millimeters and a wall thickness of 1.1 millimeters. For these simulations, the lengths of the blood vessels varied from a length of 1 millimeter to 10 millimeters to 100 millimeters. These models were then placed in SolidWorks and were run through a flow simulation where it used a new fluid that was defined as blood. The flow simulations had a flow rate of 5.6 liters per minute, which was found to be the average blood flow rate of an adult human male. And there was a second set of simulations that were run at a rate of 25 liters per minute, just to extend the worst case scenario possible for these models. Here we can see a table of the data collected from the models. This table is able to show the average shear stresses and shear strains for the models at the varying lengths, both for the simulations run at a flow rate of 5.6 liters per minute and a 25 liter per minute flow rate. This information was later transferred into graphs in order for further analysis. The graphs seen here are able to show the shear stress and shear strain of the three different materials at the three varying lengths. As you can see on the figure towards the left, all three different materials follow the same trend line. This is because stress is defined as the amount of force over the area. So with the same amount of force, all three different materials are going to show the same amount of stress. The graphic on the right is going to show a little bit of difference between the three different materials, just because the strain is now the stress in comparison to its shear moduli. In this graph here, we can see that PEEK is the material that shows the highest shear strain. When looking at the data gathered from the simulations run at 25 liters per minute, the shear stress graph is very similar to the one ran in the 5 liters per minute simulation, the only difference being that the material PEI had a different start than the other two materials. This could have been caused due to human error while running the simulations. Also, looking at the graph on the right where we can see shear strain, there is definitely a material that has higher strains than the rest. And again, because such of a large difference, this could also be due to human error while running the simulation. Taking an economic perspective on this project, the cost of material for PEEK is set to $400 per pound, while both PEI and PTFE are about $8, give or take a couple cents. In the end, the material of choice to create the artificial blood vessels would be PTFE. This polymer helps promote cell growth in fibroblast and endothelial cells, which help promote the wound healing process and help the prosthesis be integrated into the human body with the growth of endothelial cells between the existing blood vessels and the artificial one that was now placed in. In the simulations run, PTFE was able to show lower strain in every test and comparable strain to the other materials. And with its low price, it would be accessible to the general population.